So hopefully this will be the first of many ham radio projects that I want to tackle. This one's going to be an HF antenna. It's going to be an off-center fed dipole. And it's going to follow pretty much conventional wisdom on these things. And of course, you're going to need a transformer or a 4-to-1 balun or unen, as the case may be. And this one's pre-built, or I built it yesterday, and it's ready to go. I do need to test it, and that's the purpose of this video. I'm going to rig up a test bed so I can actually test this thing and see if it's going to function before I put it up in the air. And that's what we're going to do on this video. So this is a 4-to-1 balun, and assembly this is pretty much straightforward. I was going to show this construction step by step, but there's many resources on YouTube that show the construction of one of these in far greater detail than I think I could. So I'll put a link to one of those. TRX Lab is the one that I reference the most. It's probably the best one on building baluns, 1-to-1, 4-to-1, 9-to-1. I'll put a link to his YouTube page at the bottom of the screen. So this is a 4-to-1, and I'm going to be building a dipole for 40 meters, 20 meters, and 10 meters, but mostly 40 and 20 because I have a beam for 10, so I don't really need this antenna to function on 10 meters, but I do need 40 and 20, so I'm going to concentrate on those two bands to start with. So there's lots of different theories on off-center fed dipoles. This one's going to be an inverted V. So I'm going to put this up in the air about 30 feet at the center point, the feed point, and then each end is going to angle downward. And that's advantageous for a few different reasons. The single biggest reason is it helps reduce the feed impedance a little bit. And the second advantage of having an inverted V dipole is it makes it a little bit more omnidirectional. So if I have a station to the north or a station to the south, this one's going to be oriented north and south. So I should still be able to contact those stations that are north and south of this antenna, but we'll see. One of the bad things about any long wire dipole is it's fixed. You're not going to be moving it very easily, so it's not like a Yagi where you can just spin it around and move your point of aim, but it should do all right. So this is a 4-to-1. If you look up the resource material for an off-center fed dipole, a lot of people will recommend 6-to-1. And the reason they're doing that is because with a center-fed dipole, obviously, the feed point is 50 ohms. Especially if it's a V configuration, it's going to drop from what would normally be a higher impedance reading of about 70 ohms down to about 50 ohms if there's some angle at the feed point. And you know, a typical dipole in free space, what they call an isotropic radiator, where the ground isn't a factor and steel around the antenna isn't a factor. If it's perfectly flat, the feed point should be about 70 ohms. But in real life, it usually drops. It's usually down around 40, 50, 60 ohms because we're talking 40 meters. It's a pretty long antenna, and most hams don't get those things very far up in the air, and the closer to ground it is, the higher, or I should say the lower the impedance will be. So I opted, since the center of this antenna is only going to be about 30 feet off the ground, I opted for a 4-to-1 because that will lower the feed point impedance just a little bit. And if you haven't researched the theory behind off-center fed dipoles, the biggest advantage is on an off-center dipole, you're trying to pick a point in the waveform where the resistance of more than one band coincides. And you can do it off-center at about the 1/3 point, and you can also do it from the end. And from the end, the resistance of the feed point is very high. It's up around 3,000 ohms or so. At the 1/3 point, in perfect theory, it should be about 300 ohms, and in that case, you'd want to use a 6-to-1 balun. But you'd have to be way up in the air to meet those requirements, and it would have to be oriented flat also. So this one's going to be an inverted V. It's also going to be very close to the ground, so I think 4-to-1 is a better match. I'm shooting for about 200 ohm impedance at the feed point. So I've wound this. I want to test it. I want to make sure that it's working before I get it in the air. And the way that we're going to do that is we're going to feed it with a 50 ohm RF source. And I'm going to put a 200 ohm resistor across the other end of it. And if I check the SWR, and I'm going to do it on 10 meters because that's the only rig I have right now. If I do that, it should check with a fairly low SWR. And that's what we're going to do, and it'll verify that it's going to function before I put it up in the air. So here's the way I'm going to accomplish that. So I have some resistors. And it just so happens that these are about 100 ohms a piece. And I believe they're 1 watters. Not sure on that, but I believe they're 1 watters. So I'm going to be feeding this with a 10 watt rig. So obviously I'm not going to be keying up for very long because whatever I build with this handful of resistors is not going to sink a lot of current. But you can see it's about 111 ohms per resistor. So we need a 200 ohm resistor on the end of our balun so we can check SWR. So I'm going to build what's known as an array. If I take 2 of these and put them in series, that'll be 222 ohms, which is close enough to the resistance that I need so I can do some checks and make sure that the balun is going to function. However, with just 2 resistors syncing a 10 watt source, I'm only going to be able to key down for just a few seconds before these things literally go up in smoke. So we need to increase the current capability of it a little bit, and the way that I'm going to do that is I'm going to add some more resistors. So if I put 2 more in parallel, we have 110 ohms and 110 ohms. The whole thing is going to be 222 ohms. We'll have 110, 110. In series, it's 222 ohms, and if we put that in parallel, now we're back down to 110 ohms. Well, that's not going to work. So we're going to have to add some more resistors. So will this work? So if I take 4 110 or 111 ohm resistors, put them in series, that's 444 ohms. And then if I put those in parallel with another branch circuit, we'll cut that in half and it'll be 222 ohms. So that should work. So that's what we're going to rig up right now. I just got this little circuit board here that I can shove the resistor legs through, solder them in place, run a couple leads to it, and we'll be up and running with our test bed, hopefully. So I'm going to do that right now. Close enough. All right, we have an SO239. Now this will be what mounts at the top of the mast, and we'll run our wires through these little holes, and up and around this, and then out. So our SO239 is going to sit like that. And this is a sealed enclosure. It's got a nice foam gasket with the lid, so these can be had at any good hardware store for about $10. Okay, time to test. Okay, here we go. This is a coax jumper coming off the radio. And I'm just going to go ahead and attach this to my SO239. And I'm going to turn the radio on. And then I'm just going to leave it in SWR to start with, because I want to watch my SWR reflected meter right here. And I'm just going to quickly key up with the mic gain all the way off, the radio on AM, and I just want to watch that needle and see if it slams the other side real quick. So here we go. Okay, you can see it barely moved. Okay, now I can go ahead and calibrate. And this transformer is working perfectly. It barely moves the needle. And always remember, never touch open RF when you're transmitting, because you could get an RF burn. But now that I've done that, and now I'm not transmitting, I want to see how warm these are. And they're not really that warm. Just barely warm. So okay, this was a successful test. I'm going to go ahead and assemble this and probably get it up in the air here shortly. Okay, so our transformer works, and I'm going to set this aside. If I ever decide to build another 4-to-1 or 4-to-1 balun, this will come in handy. So I did that the kind of a redneck way. There is actually a formula for this, and it was discovered by a gentleman named Kirchhoff. And I was just talking to him the other day, my buddy Kirchhoff, and he was explaining to me the formula for doing parallel resistance, and he calls it his current law. But of course, Gustav speaks German. I didn't understand a word he was saying, but I did catch him writing on the chalkboard, and this is basically what I took away from that. So whenever you have a bunch of parallel resistances, so let's say we have a voltage source, and we have a run of 4 resistors. And then we have our load on the other side of it, whatever that may be, or we can just call it a ground, because our ground is essentially, or our load is essentially a ground of some sort, whether it be a motor or an antenna. Might not be a perfect ground, it might be a resistive ground, like 50 ohm antenna, but there you have it. So anyway, Kirchhoff's current law says that if you add up the individual node currents in all of these resistors, you will have the total current through the circuit. So there's no current lost. And the voltage, of course, if you have 12 volts up here, let's just say we have 12 volts. If you check each one of these nodes, of course, we're going to see the same voltage. Voltage stays the same, but current through each individual leg is a split of the total current of the circuit. And you can have different value resistors here. I made it simple with this. These are all the same. So it was easy enough for me to just lay it out on the table here and figure out what the total resistance is going to be. But what if these are all different resistors? Be a little bit more difficult. And there's a formula for that. So this is how I remember it. There's other ways to remember it, but 1 over R1 plus 1 over R2 plus 1 over R3, etc. is equal to the resistance in reciprocal. So you can solve for RT, but I find this easier to remember. So if you can remember this, then you can just use the reciprocal function on a calculator to get your total resistance and figure out what this entire circuit would act like as one resistor. And that's really what you want to know. Once you know that, you can figure out what the current of the total circuit is going to be. And you can also figure out, in the case of antenna work, what the total resistance is going to be. In this case, we needed 200 ohms-ish, and we ended up at 223 ohms, which, as you can see by the SWR meter, the radiator was perfectly happy with that. So this is Kirchhoff's current law. He also has a voltage law, but I'm not going to go into that right now. So anyway, let's put this together. We'll start with the SO239. Oops, I'll take that off. Now you notice these eyelets are a little bit too long. I'm going to shorten these with a hacksaw, because the more they stick out from the box, the more leverage they have. The closest they are to the box, less leverage. These are very sturdy boxes, but I still put the eyelets as close to the corner as I could get it, because the strongest part of a box is the corner. So you might think, why didn't I just go buy an off-center fed dipole or end-fed dipole or a regular dipole? And the answer to that is that I believe that the amateur radio hobby is all about building it yourself, if you can. So I've been tinkering with radios off and on for about 35 years, and learning more and more as I do that. So this isn't my first foray into experimental antennas. Some of them have been successful, some of them have not, but that's how you learn. Antennas in general are a challenge because there's so many variables. Whenever you hang an antenna in the air, it's interacting with everything that's around that antenna, whether it be the metal roof of your shed or the trees in the backyard. Not to mention that the components that you're using, as far as wires and connectors, all react differently. So larger wire will react differently than smaller wire. Different materials react differently. So aluminum reacts differently than copper. Copper reacts differently than stainless. The wire I'm going to be using is just simple stranded wire that I robbed from an old extension cord. And I've got enough of it that if I make a mistake, I can recut it and try it again. Okay, so that's basically what we're dealing with here. I'm going to be feeding some of this wire through the loop, and I'll attach it to the loop And then I'll run it up through that hole, and I will connect it with this lead, and this will be glued to the bottom of the box. And then I'll do the same thing on the other side. Off-center fed dipoles have one short leg and one long leg. I'm going to start with 68 feet for 40 meters. I'm going to take 1/3 of 68. Oops, I don't know how I did that. 68 divided by 3 equals, so approximately 22.5 feet. So the short leg is going to be 22.5 feet. The long leg is going to be about 45 feet. Let's see, 22.5 times 2. Yeah. So roughly 45, maybe a little bit longer than 45 feet. I'll be very precise when I do those cuts, because once I start checking the antenna up and down the band, let's say that I've cut it too long, and I check it on a band. Let's just pick 20 meters, for instance. Let's pick 40, because you should tune for the longer bands first, I believe. So I check it at 40, and I check the bottom of the band, I check the top of the band, and I check the middle of the band. And as the frequency decreases, the SWR gets better, which tells me it's too long. So I want to set it for the best WR at the middle of the band. So I would then shorten each leg, not the same amount, because it's an off-center fed antenna. So I would shorten the short leg 1/3 as much as I would shorten the long leg, which would be 2/3. In other words, if I took 1 inch off the short leg, I would take 2 inches off the long leg. I'd just keep shortening it in an equal amount until the SWR fell where I needed it to be in the middle of the band. And then once I get it reasonably close, I'll check it on 20, and hopefully it's close there as well. If I make a mistake, then I just either add some wire to the end of it or just start over with a new piece of wire. And just keep going back and forth until I find the best compromise as far as SWR and the frequencies that I want to talk on. So I could have put up a regular dipole, and I almost did, but a regular dipole fed at the center is only really good for one band, and that's the band you cut it for. So if I wanted to do 20 and 40 meters, I would have to do 2 dipoles, which you can do. They're called fan dipoles. You just feed them from the same source, the same point. But when you get that up in the air, that is a little bit more conspicuous than 2 wires, because you're going to have 4 wires, you're going to have separators between the 2, and it's just a bigger undertaking, and it's a little bit more of an eyesore. So I think I'm going to try. It's still an option for me, but I think I'm going to try the off-center fed dipole to start with, see if I can get the SWR where it needs to be, and make my decisions from there. So this will attach with a normal PL259, like so. And since this box has pretty good sealing, I don't believe that I'll need to waterproof it at all. It's a pretty good little gasket. It'll seal up really nice. I'm just going to mount it to a piece of 1x1 square tubing. So I'll drill a hole here, drill a hole here. I'll probably shoot at least 1 screw through the center. Mount it to that. That'll mount to my tower, and then I'll hang my wires. Oops, hang my wires off of each side, like so. And that's the plan. And I'll keep you updated on how that works. Maybe even show you an SWR check once I get everything up and going. Thanks for watching.